Greetings. We shall be presenting Project 8, which is the space-time computation of the electromagnetic fields and the potentials generated by moving point charges. The contributors to this paper are Devansh, Arjun, Archit, me, Ayushman, and Jason. Right. In the very beginning, I'll first read out the abstract of the paper. So this paper presents a computational method to directly calculate and visualize the directional components of the Coulomb, radiation, and total electromagnetic fields, as well as the scalar and vector potentials that are generated by moving point charges in arbitrary motion with varying speeds. This method explicitly calculates the retarded time of point charge along a discretized grid, which is then used to determine the fields and potentials. It can also approximate complicated time-varying continuous charge and current densities. Several example application and lab experiments are simulated and discussed, including electric and magnetic dipoles, oscillating and linear accelerating point charges, synchrotron radiation, and brainstorm. So, coming to the introduction, the electric and magnetic fields that are generated by moving point charges are often complex and unexpected compared to the static counterparts, which is the electric and magnetic fields generated by a static charge. And in particular, for moving point charges, there is a correction to the retarded Coulomb field, which is proportional to the rate of change of the retarded Coulomb field multiplied by the retardation delay. Also, if the charge is accelerating, there is an additional term in the electromagnetic field expressions known as the radiation field. We shall see all of this in the plots that are going to follow. Retarded potentials and these solutions generalize Poisson's equations to account for time dependence and retardation effects. And unlike the case of Maxwell's equations, these potentials have a freedom of gauge choice where the potential need not satisfy causality. However, the physical fields that we derive from these potential fields must satisfy causality. There are only a very few known cases where an analytical solution for such potentials exists, and these often involve fairly complex vector calculus and hence can be very difficult to visualize. There are no well-known approaches to computationally solving problems with moving charges directly in space and time. However, one could ask what is the motivation behind studying these, and that's because a lot of people argue that these are much more fundamental than the physical field counterparts of these. Say, for example, these are fundamental in explaining peculiarities like the Aharonov bomb effect. And therefore, to address this gap, this paper developed a direct numerical method modeling technique, which is implemented in Python to solve problems of moving point charges and calculate retarded times. Therefore, this program allows the user us to directly visualize how these different EM fields and potentials are formed using numerical methods to determine the retarded time of the particle at different points in space. This method that we're studying is not only academically very relevant, but it's also crucial for many practical applications in many high energy electron experiments like the electron energy loss spectroscopy, EELS, or even the vortex EELX. The structure that we'll be following for this presentation will be as follows. First, we shall go with the theoretical background of moving point charges in electrodynamics, where we'll include the Leonard-Wishart potentials and the expressions for electric and magnetic fields. Then after that, we'll show a selection of results and examples that can be studied of the computational code, which is also given in the paper. That shall include the EM field generated from a fast oscillating charge and from an oscillating dipole, as well as from steady state and time varying current sources. After that, we'll also explore the phenomenon on synchrotron radiation emitted from a moving point charge with constant acceleration, and brainstorm effect. And finally, after that is done, we shall also show a few more cases that we have added ourselves, including orbiting dipole, rotating dipole, alternate charge current loop, so a current loop which has positive and negative charge placed alternatively, and a particle accelerating, then following linear velocity, and then decelerating. We've also created a separate class for this that shall be talked about towards the conclusion of this program. So I shall quickly run through the basic math or the basic theory behind a moving point charge for their EM fields. So given we have a point charge q at a position r0, which is a function of t, so r0 keeps varying with t, and velocity v, the charge density will be rho naught delta r minus r0 t, and the current density will be rho naught v delta r minus r0 t. And when we consider the Lorentz gauge, the scalar and vector potentials of a moving point charge are known as the Leonard-Wishart potentials, which are given by VRT, which is 1 by 4 pi epsilon naught into QC by NC minus V dot N, and ART, which is mu naught by 4 pi QCV by NC minus V dot N, which simplifies to V by C square into V. The physical, electric, and magnetic fields generated from moving point charge, which these are gauge invariant by the way, can be obtained using various approaches, and we derive them directly from the scalar and vector potentials. The reason we're skipping through the math and not delving deep into it is because all of this has already been derived in class. So we're allotting more time for the later parts of the project, which is the plots, the code explanation, and the code documentation and the conclusion. The electric field comes out to be q by 4 epsilon naught v by n dot u cube into c square minus v square into u plus the vector triple product of n cross u cross a, and the electric field will the magnetic field will be 1 by c into n cross e. And as we can notice here, the first term, which is q by 4 pi epsilon naught into this is actually the electric coulomb field as written here. And the second term, so this entire thing into the vector triple product of n cross u cross a, is the electric radiation field. And this is linear. The electric radiation field is linearly dependent on the acceleration a, while the electric coulomb field is independent of acceleration. This shall make more sense in the plots. And all of these equations that we have seen here are calculated at retarded time t dash, where t dash is given by t, the normal time, minus r t dash, r is a function of t dash by c, where r is the distance between the observation point and the retarded time point. So now that we've laid down the mathematical fundamentals for this, my teammate Devansh will now further explain the code and the code documentation. Alright, that's it. Thank you.
Hello, I'm Devan Satra and I'm going to be explaining the code of our project. So first I'm going to start with the main code that we use in our project, that is charges.py and field calculations.py. All of the figures that I reproduced are based on these two files. So I'm going to run through these two files first, and then I'm going to explain I'm going to explain one example and how exactly these two are used to present the fields. So firstly, charges.py. So in this Python file, first we define a class named as charge, which is an abstract class where the kinematics of the charge is defined. These are defined as parse right now because we'll define subclasses which will actually define how the motion is of each particle in different scenarios. So the first one is oscillating charge, as suggested by the name. This is pretty self-explanatory. So basically we have these attributes for this class. So we can define the positive charge. Basically, if it's true, then the charge is positive, and if it's false, the charge is negative. We can define the start position. We can define the direction, basically the XYZ. In what direction will the charge oscillate? And then the code automatically normalizes it to unit length. We can also define the amplitude of oscillation, the max speed of the oscillation, and start zero just means that if true, the charge starts from rest, and if false, it starts at whatever velocity you define it to be. And then if applicable, the stop t will decide at what time the oscillation stops and when do you want to stop the animation as well. So as explained, in this example here, the start position is defined to be minus 2 nanometers in the x direction, and the direction of oscillation is the x direction as mentioned here, and the amplitude of oscillation is again 2 nanometers, and the max speed is defined to be 0.9 the speed of light. So the x position, as mentioned, is just the harmonic oscillator equation in the x direction, just with 1 minus cos omega t, because the particle starts at the minus x max position, and then all of the other ones are defined according to that. So if you have the direction as 1 here, so this will change to 1, and then accordingly everything will be defined like that. So it depends on the arguments that you give here, that your motion will be described by these methods of the class. Same for the velocities as well as the acceleration. It's all just predefined functions as defined by our arguments that everything will be calculated. Uh, the second is orbiting charge. Basically, this means that the charge is moving in a circular path in an orbit that is predefined. Uh, Here, the methods are just same: positive charge, amplitude, max speed, start zero. The only change is here phase. The phase means the regular thing. So, if it's zero phase, it starts here. If it's pi by 3 phase, then it will start 60 degrees to the x axis. Uh, so phase just means that. So if you want to define multiple charges, so you can have phase difference between those charges in a circle. Uh, so similarly, the x is defined as amplitude times cos omega t plus phase, and y is defined as sine omega t because x and y direction defined like that. And one important thing to note here is that the motion is only defined in xy axis. Obviously, you can change this to be however you want, but that is the most general thing that they have done here. So the motion is in just one plane. Uh, and similarly, your velocity and acceleration are also defined similarly. Uh, the third class is oscillating plus orbiting charge. So this is basically a charge moving in a circular orbit but oscillating at each position, so it's moving like this. uh, Here also the attributes are almost the same. uh, the only change is you can define a angular frequency of the orbital motion instead of the uh, max speed and everything like that that you did in the first one. uh, so here you can define the uh, angular frequency of the orbital motion and the amplitude of oscillation at each point, which is defined by max speed divided by the radius to omega. Um, so similarly, so basically this is like outside its circular motion defined by the cos, and then inside again you have cos omega t plus phi, which defines the oscillatory motion on the circle itself. As you can see, y is sine and then inside it's cos. And again, this motion is also defined in the xy plane. So this motion is also defined in one plane. You can change it however you want in the code. Uh, Here you also have a get period function. Like you had a get period function in all of them. I forgot to mention, which is just 2 pi divided by omega, which is used in the calculation later on. So the third and fourth methods are obvious. It's a linear accelerating and linear decelerating charge. So if it's just like one motion, one particle accelerating in any direction, which is defined by that. So the kinematics are pretty straightforward here. So I don't think I need to explain that. So I'll be yeah. There's also a charge, linear velocity charge. So if it's moving in just one direction with no acceleration, just a fixed velocity, that's also defined there. This is a class that we defined on our own to expand on the paper. Linear accelerating decelerating charge. Uh, Basically, this is the motion where initially it will accelerate for some time, then it will stay for constant velocity, and then it will decelerate again to zero speed. So we have defined that since it gives some very interesting results, which you will see later on. Um, so here the we have just considered moving in the x direction, and because we can say that without loss of generality that we can just define the x direction to be the direction of motion. So we've just defined the kinematics in the x direction, and everything else is 0 in the uh, y and z direction. So as you can see here, for you can define the time interval of acceleration, constant velocity, as well as the deceleration time, and according to that, uh, you have you basically have your equations of motion, which is defined like you can see in the code. Basically half at square plus constant velocity, and then when it's decelerating it's minus half at square, like similarly like that. So let's move on to the other file, which is the main file where all. So now I'm going to be explaining the field calculations.py code, and basically the overview is that it uses the linear Wishart potentials as well as the uh, so basically it uses the linear Wishart the potential formulation to the electrodynamics, and then calculates the fields and everything through that. So basically you have these methods in your uh, moving charges field class. Basically you define the charges which is mentioned in the previous charges.py file, and then you can call all of them in this class using this constructor. uh, Basically after that, uh, and h is just some tolerance level for numerical optimization. So this is basically like the number uh, smallest number which is error in the calculation. So it's set to a very small number to achieve high precision. After that, as mentioned, the calculate E field, that is that just uses the Newton-Raphson method, uh, and calculates the field using the self.calculate individually, which is the main calculation as mentioned. So it uses the equations from the potential formulation exactly as same as mentioned in Griffiths, and just uh, outputs that to this function, which does the convergence through Newton's method, and then outputs the field at each and every point in the xyz plane, uh, which is created by the mesh grid function above. Uh, so the same is done for the E and B fields as well as the potential. So the equations are obviously the same as before, and then one more thing that they have done is calculated the Pointing vector, which is just 1 by MUC mod of E square as mentioned in Griffiths again. Uh, so now I'm going to run through an example, uh, figure 2, where it's used to uh, display an actual field for a figure. So basically in this, it's just an oscillating charge at oscillating in the x direction. Uh, Basically what you do is that you define the charges in a variable known as charges. You can define as many charges as you want here. In this case it's just one oscillating charge, uh, and then you define your start time to be 0 or whatever you want to define it as, and then you define your xyz as your mesh grid again as mentioned before, uh, and then you just input that into the field, into the function moving charges field, uh, as your method, and then you calculate the field from that. Uh, as I mentioned, there are two different types of field, which is the acceleration and the velocity field, which is the radiative and the Coulomb field. And then we also calculate the addition of both the fields and then display all three of them in different columns. So all of this code is just for the plotting, so where each of them will be there, and you define multiple axes for plotting it in different places. That this is just code for that, and then In the animation, it's almost the same. The only difference is that we define frames, different frames at different times, and then you calculate the field at each frame, and then you just play the whole thing in one go. So yeah, that is it for the code.
I will now be showing on how to introduce a new class into the charges.py for your own specific cases. Currently, we have 5 subclasses: oscillating charge defined in the paper, an oscillating charge which moves left and right, or up and down, or in and out of the plane as specified, given the start position, direction, amplitude, and so such. An orbiting charge which moves in a circular fashion, an oscillating orbiting charge, a linearly accelerating charge, a linear decelerating charge, and a linear velocity charge, uh, which moves in a straight line with a constant velocity. So it's very easy to create a new class. All you have to do is define uh, an initialize function by and define the necessary parameters in the charge function, such as whether the charge is positive or not, uh, whether uh, what is the x position at any given amount of given time. So note that t is which is given in will be an numpy array. So you cannot use if statements define define what the function to define where the charge is at what time. And it's much since numpy arrays don't work with if statements very well. So rather than that, something like this would work, where I have defined that the x position is 0.5 times the acceleration times t square, but immediately after I've defined that given after a certain amount of time the x position is defined in a different way. So this allows me to have the x position defined till ACC of impulse time, and a new so and a new function for when it's after ACC of impulse time, acceleration of impulse time. So right now, what these two are meant to do is that x position is supposed this first one is supposed to denote that the charge is accelerating from time 0 to infinity, while this one is overwriting it, telling that over this acceleration impulse time the charge starts to move at a constant velocity, and this one tells that over a given time, which is the deceleration impulse time, that the charge starts decelerating, and that over a certain given time that the charge stops. This is telling that the charge is at position 0 before the time before the where for t less than 0. Similarly, I have to define the y position, z position. In our case, it's both 0. The x velocity in the similar fashion. So the x velocity keeps increasing as time at t greater than the impulse time. It's set to a constant. At over the deceleration time, it starts decelerating, so on. For same has to be done for the y velocity and z velocity. And now the last part will be just for setting your acceleration, x acceleration, defining x acceleration, y acceleration, z acceleration. These the y velocity, x velocity, and x acceleration have to be computed by the coder beforehand. The computer does not figure out the velocity and the acceleration from the given position. So you can so that's a slight drawback, but it's good enough. So I've used this. So I've added this class and made figure 20.py, oscillating along the x-axis with a max speed of 0.5 c at the origin and an amplitude of 2 nanometers. Uh, Here the figure we have chosen here is an XZ slice of the 3D system, and we are only showing the magnitude of the electric field currently. This is one of the snapshots in time when the charge was situated at the origin. We can see that the yellow regions denote more higher electric fields, while the blue regions denote lower electric fields, and the arrows give the direction of the electric field. We do not have any EY fields while in the XZ plane for due to the charge only staying in the uh, staying on the x-axis the whole time. So the we this is the first figure. The second animation shows us the fields EX, EY, EZ fields in the YZ plane and the BY and BZ as well. So these are in the YZ plane. So the charge is moving out in and out of. So you can see that the charge is moving in and out of this plane. So as it moves in, there's a net positive field, and while moving out, there's a net negative field. If it's not visible here, there is negative signs at the bottom. So blue means negative here, while yellow means positive. Here we also I'll go through the code. In the code, we just define a class called oscillating charge for figure 1. So we are choosing a positive charge and its direction to be in the x-axis. So 100, the start position of -2 nanometers and a max speed of 0.5 c as it reaches the origin. The amplitude is a default parameter given in the charges.py with over here, where the amplitude is given to be 2 nanometers. Here we can calculate the E field, the B field, the acceleration field, the Coulomb field, the radiation field using field.calculate. And once we do that, we just plot the fields. In figure 2, we do the same. It's just since there are a lot more plots, there's a little bit more code. Emax and Emin give you the minimum and maximum scales in the plot. So we choose 10 power 7 and 10 power 5 since for an appropriate choice. Yeah. So this is the EM fields. This is the total field, the Coulomb field, and the radiation field. Notice how the radiation field is 0 in the start. This is before the charge starts moving, while the Coulomb field does exist before the charge starts moving. This is in the XZ plane. So the charge is moving in the x-axis, and the z-axis and y-axis act as the same, symmetric. This is a plot of the potentials. We have only chosen AX in the vector potential, phi, and the pointing vector which can be calculated using E cross B. Here we can see that the pointing vector shows us how the energy radiates out of the system. This also can be easily calculated using the function calculate potentials, where we get by choosing V, Ax, and Ay, Az, we can easily calculate the potentials, and calculating the pointing vectors is also very easy. Yes, you use field.calculate pointing, which are all given in the field calculations.py. Our next case is the oscillating electric dipole. So in this case, we have a dipole of one positive charge and one negative charge, and they start on at -2 nanometers and +2 nanometers. So charges are at -2 nanometers and +2 nanometers, and they start to oscillate like this. So the dipole switches its direction uh, in some time. Its maximum speed of the maximum speed of the charges is 0.5 as they reach the center, while their angular frequency is about 7.5 in 10 power 16 radians. So this is a plot of their total total fields, Coulomb fields, and radiation fields along the xz plane. This is the this plot shows the ex field, ex component, ex component of the E field, the y component of the B field, and the z component of the B field. It's the code is also simple for this. We rather from before, the only change from before is that now we, rather than having one charge, we start out with two charges, one with a positive charge, another with a negative charge, one with direction in the x positive x, one in the negative x. Starting position of this being -2 nanometers, its starting position of the other one being 2 nanometers, while both of them have a amplitude of about 2 nanometers by default. Next, much is mostly about plotting the data we get. This is a whoa. This is another fear. This is an attachment to the previous one. This calculates EX, EZ, and BY in the same XZ plane. This calculates the potentials, and you notice this shows a negative positive potential on the left and the negative potential on the right, denoting that the positive charge is on the left and the negative charge on the right in the start. And we do notice that the pointing vector is predominantly in the z direction. It's not that there's it's not that there's no radiation in the x direction. It's just that it's much less than the z direction radiation. So that's why, since it's lesser than 10 power 10, it's not showing much, but it is there.
So the next case discussed in the paper is of synchrotron motion, that is charged particle moving in a circle. As you know, circular motion is accelerated, so you do expect to see some kind of radiation, which is what we observe. So right now what we simulated is, or rather what the paper simulated is that charged particle moving in the xy plane in a radius of 2 nanometer and at 0.5 c. It's relativistic so that we can see the effect within the bubble. As you can see, the outer bubble expands as c. So to see something, we need to move at relativistic speeds. Yeah. So this is the xy plane of the system. As you can see, in the xy plane also we'll see sinusoidal motion similar to that seen in just a electric field, just a particle oscillating. But the only difference is that the center of mass is not the center of mass, but the origin of the radiation moves slightly because the intersection point with the plane is different. So there's nothing interesting here, but the real interesting case comes when we look at the xy plane, in which we see this distinct spiral pattern, and we can see that the radiation goes as a spiral, and that was not observed anywhere else, which is expected, and it's good to know that power is radiated like this. For the power exactly, they have calculated the
pointing vector as well, and you can clearly see that the pointing vector, at least in the xy plane, moves as a spiral outside. These are the vector potentials and the scalar potentials. So yeah, that's, I don't think there's anything else in this case. Right, so the next case they have discussed is current loops. Oops, this is the paper. Yeah, so the next case they have discussed is the current loop, in which so this is the first example where we see a continuous charge distribution being discretized. So what they did was they they split the current loop into n charge particles moving at 1 meter per second. The total charge in all, so n was 16, 64 and 256. The total charge in all three cases was 256 e. So the current was about 6.5 into 10 raised to minus 10 amps. They put the charges at equally spaced uh, phases on the ring. So each charge is at 2 pi by n. And yeah, so now we can see that the accuracy of the distribution is increasing as we increase the number of charged particles, which is expected. And you can see that the magnetic field also becomes positive inside the circle and negative outside, which is what we expect from a current loop. Like current loop has a constant magnetic field inside. So they have plotted the errors of the system as we increase the number of particles. So they have so the system is symmetric about a 2 pi by n rotation. So you will expect that all the error is in this part, like in between the two particles is where we see the error. So they plotted the magnetic field in between the two particles, and you can see that for 16 the error, not the error, but like you would expect a constant magnetic field inside everywhere on the circle, but you can see, but as you can see for the 16 charge particle case and the other case as well, you can see the magnetic field slightly changing as we move along the circle. So that is what they have plotted here, but you can see that the approximation holds really well for the 56 charge particle cases, even though it doesn't hold for 16. And this error is also quantified with the relative error. So they just took the statistical error. Standard deviation is root of sigma xi square minus x bar square, uh, and they plot the relative error that divided by the mean. So you can see that the relative error is 1%, uh, 1% at around 7 for 16, but it's at around 9.5 for 18. So 1% error at 9.5 radius, and it's around 10 raised to minus 6 error at the origin. So which is really good uh, for the discretization. So it just shows that the discretization will work. Uh, yeah. Then this point was at 9, not exactly 10, but 9.9, like this plot, right? So yeah, right. So the last case discussed in the paper is linear acceleration and Bremsstrahlung. So they discussed both the accelerating and decelerating charge particle case. This is the accelerating from rest, and this is decelerating, and this is decelerating. So yeah. Uh, So the decelerating case, to see a difference, they took the charge to be at 0.99 C, and then starts decelerating. So at 0.99 C, you can see that the electric fields are squished in the perpendicular direction, and they are like highly squished. So, and you can clearly see the shell of Bremsstrahlung, like radiating outwards. This is the total field, Coulomb field, and the radiation field. As you can see, there is no radiation field when it's moving at constant velocity, but as soon as it starts decelerating, it has uh, the field is there. So as you can see, the sign also flips between acceleration and deceleration for just the radiation field, because that's the only field that's dependent on the acceleration of the particle. So yeah, these are all the cases discussed uh, in the paper. And in addition to this, we have also uh, added a few more examples of our own, which we will discuss.
Hi, my name's Archit. I'm going to go over the piece of code that we did ourselves. So here we've implemented a few cases of moving charges on our own so that we can visualize their EM fields. First, we have an orbiting dipole where the dipole is moving about some point which doesn't lie on the dipole's axis, and the angular separation of the charges along the circle of movement is about 30 degrees, which is why we get to see some interesting patterns here. So if you look at the EX field, you can see that it keeps flipping directions at the same frequency as the movement of the dipole. This can be understood quite simply because if you imagine the dipole while it's near the right end of the circle, then you're going to have if you imagine the dipole as it's approaching the right end of the circle, right? So you have a plus charge here and a minus charge here, and they're moving in this direction. Then the repulsive field or the charge from the plus charge is going to be greater, and therefore you'll see uh, you'll see a green contour in this direction, right? But as they move along, the negative charge is now closer to this point, and therefore you'll see a negative contour, a blue contour heading towards that, right? And that's what we see clearly in the EX field. We also see something similar for the BX, BY, BZ fields. What's also interesting here is that you can see that because the dipole is not rotating about its own center, the point from which the EM fields keep changing, as you can see in any one of these plots. What you also see here is that what's interesting to note is that you see EM fields only originating from 2 points, and that's because in the code we've taken the fields in the XZ plane. So we only see phase changes in particular when the charges cross that XZ plane, right? So this is these are the fields in the XZ plane. We also plot out the fields in the XY plane, and here we see something very interesting as well. We see spiraling, which is similar to this figure in 10, where you can see a point charge moving about a circle, and here you can see the vector potentials produced by that point charge, right? So consider this particular field where you look at the potential contours, right? So at every point on this contour, you have the given value of the potential, and then the electric field is simply the gradient of that. So how it varies at any point, right? And that translates immediately to here. So as you can see, because you have an orbiting dipole, right? So yeah, as we can see, the orbiting dipole seems to have an interesting field near the junction of where the fields are being emitted from, EX, EY, and EZ. We'll compare this to the fields that we get from the rotating dipole in the XY plane when we get to it. Right, but as we'll see, the phase difference of 30 degrees versus a rotating dipole, which is rotating about its own center, which has an angular separation of 180 degrees, has a very different sort of contour near the center. Right. Moving on, we see here the rotating dipole. Right. The rotating dipole has some interesting contours. Consider the EZ. Consider the EZ in the XZ plane. Right. We can compare this to the second figure, where you have a sinusoidal motion of the charge along the x-axis. So at first glance, it isn't obvious that you could compare a sinusoid to this rotating dipole, but if you think about it, a rotating dipole simply has the charges moving in a circle, which because the circle is small enough, you can think of it as the charges are essentially moving forward and backward along the circle, right? So there's not too much difference of in the magnitudes of the field along the XZ plane. So yeah, so as you can see here, to draw attention to the second figure. As it's moving along the xy plane, you see here that you have in the positive z plane, you see that the field is going away from the charge, and in the negative z plane, it is also going away from the charge, but it is negative in magnitude because uh, it is minus z, correct. So if you were to think of having two such charges, man fuck. Okay, next we have the rotating dipole, where the dipole rotates about its own axis. So the angular separation in this case is simply 180 degrees. As you can see, if you were to look at the EX fields in for this rotating dipole, you can see that the the sign keeps changing in the center, and that makes sense because at one point uh, you can think of the dipole being in this orientation where you have a plus charge here and a minus charge here, and then after half a time period they switch places, and so the sign has changed, and therefore you see this change in phase for the EX field. You see something similar for the EY field as you're looking at the fields in the EXZ plane, right? Uh, right. Moving on, here we see the rotating dipole, but in the xy plane. And compared to the orbiting dipole, as mentioned before, you can see that the spiral originates from the center and is much more symmetric as compared to this orbiting dipole, where you can see that even the center moves off. Is the center of the EM field is slightly off center, right? Here you can also see that the phase in the center keeps changing, and again that makes sense because initially you have the positive here and the negative here, and then after half a time period they flip places, and therefore you have that change in phase, change in sign, right? Moving on, next we have this alternate charge current loop, which is in the realistic system, but we thought it was cool and therefore implemented it. So here you have n. Here you have so for n is equal to 16, you'll have 8 positive point charges and 8 negative point charges, all of equal magnitude, moving around in this circle. As we can see, as one might guess, also quite clearly, as you increase the number of point charges in the ring, the fields simply go to 0, and this is quite logical because uh, as you have alternating point charges, the fields everywhere just sort of cancel out to 0, and therefore with more point charges it becomes a better approximation for 0 charge, which is quite obvious here. You can also see a little distortion in the rings for the EX and EY fields, and that's simply because as it's moving, it makes sense that uh, the fields are slightly shifted in the direction that they're moving. Right. Okay. Next we have the final case, which is acceleration and deceleration. So initially you have a charge at rest, which then accelerates, uh, and then moves at some speed, moves at a constant velocity for some time, and then decelerates, right, until it reaches rest. So comparing this to the Bremsstrahlung along that we saw before, as you can see here, right? So as you can see here, the EM fields start to originate, and there is a very clear phase gap in how you would join the electric fields. But let's look at this. Let's look at this case, right? So what's also very interesting to notice is you see these green circles here, which just mean zero field, and that's because there is no radiation component to the electric field when it is moving at a constant velocity. So in this 10 seconds, the charge moves for the charge accelerates for one third of the time, and then constant velocity moves at constant velocity for one third of the time, and then decelerates for one third of the time until it comes to rest. Here it also looks like in the 1, 1 plot, in the ex plot, for the total ex, you can see that it almost seems as if the point charge is moving backward uh, as the field is emitted, but that's simply because, as in Bremsstrahlung, right, which is the braking radiation, the EM field keeps originating as if it were being originated from a point charge that was continuously moving, which is similar to the reverse case where it starts accelerating and it seems as if the field was coming from a stationary point initially. Right, as you can see here, the circle is centered about the zero instead of wherever the point charge is. Right, that's all. In conclusion, we were able to simulate a whole lot of cases, as can be easily picked out from this drop down menu that we've also implemented. Right. However, the one drawback of this entire package is that it does not account for interactions, and so you can't have uh, multi-particle simulations, multi-shard simulations. Yeah, that's all. Thank you.